Hello everyone, I hope you people are doing fine, staying safe and studying at the same time. Okay, so welcome to the next video chapter on the thermodynamics. So today we will be taking a look into various aspects such as the work done in a reversible process is going to be maximum. Further, we are going to take a look into the heat energy, the temperature. We are going to take a look into the heat capacities, specific heat capacity, molar heat capacity, the relationship between the specific heat capacity and molar heat capacity. So before starting with that, we will start with the first concept for the day, and the first concept that we need to deal with is the work done in a reversible process. Alright. Now they claim that the work which is done in a reversible process is maximum. Okay, so they are claiming that this particular work process is maximum. Okay, so they are claiming that this particular work done in a reversible process is actually maximum when we compare to that of the work which is done in an irreversible process. Now we need to prove this point. Okay, so in order to prove this point, let us say that we have a particular cylinder. Let's say that this is one side of a cylinder. Let's take this one over here. Alright, so let's say this is an opening of a cylinder at the other end. Right? And let us say that this is a cylinder that what we have. In order to prove about the work, let's set a piston to it. Okay, so if we are going to set a piston to this, let us say this is a position of the piston as what I am speaking about. Okay, now let's say this is the piston as what we have here. Okay, so when a work is done, usually the equation for the work is given as work is equal to minus of external pressure into the change in the volume, right? This is what we have. Now, in order to say that the work is maximum, then whatever the pressure that we subject at this particular point over here, these forces or this particular pressure at this point should be maximum, right? So in case if the external pressure that we are going to apply on the piston is maximum, if this is a condition, then what will happen? The work which is done is going to be maximum according to this, right? Because if this particular thing is going to be maximum, of course, the volume that is going to be changed is going to be maximum. So the product of these two is going to give rise to the maximum work which is done, right? Now, let us say that this is a reversible process. Now, in order to take a reversibility condition, okay, let us say that whatever the external pressure that we are going to subject over here is infinitesimally smaller than the internal pressure. Now when I am saying internal pressure, that means the pressure what is there over here because of these gases, right? So let's say this is the internal pressure, correct? Now if the condition is achieved such that the internal pressure is greater than external pressure, then it is going, this particular piston is going to move back. Okay, expansion is going to occur. Now, if the condition is such a way that this particular thing, that is the external pressure, is smaller, but Px is infinitesimally smaller, that means, let us say that internal pressure is 1 atmosphere internal pressure, external pressure let me say as 0.99 atmospheric pressures. Okay, so the difference between these two is very small, right? So at this particular condition, a piston can either go inside or can either come outside if there is a small change with respect to pressure, right? So here the condition is that if your external pressure is infinitesimally smaller than the internal pressure, this will give rise to, this particular thing will give rise to reversibility condition. So when this particular reversibility condition occurs, that means you are doing a work in order to get this piston inside, at the same time the work is done in order to get the piston outside. So there is a reversible condition, right? That is the expansion and the contraction with respect to the piston. Okay, now when we have a reversibility condition, that means the work which is done at this reversibility is nothing more than work done in a reversible condition. Okay, and the work which is done maximum at this particular point is work done is maximum, and at the reversibility condition these two things are going to become equal. So whenever there is a reversible process, the work is usually maximum, and this is how we predict about this. Okay, so I hope you understood about this particular concept. So when there is a reversibility, what is happening? Some amount of work is done in order to compress the gas, some amount of the work is done in order to expand the gas. So there is a dual process which is occurring at the same condition of reversibility. So at the point of reversibility, two types of work has been done. So therefore, the work becomes maximum at that particular case, and thus work is maximum when the particular process is reversible. Okay, so this is what we can conclude with this. So let's start with the next concept. The next concept that we need to deal is how about the work which is done in a free expansion. Okay, of course, it's free expansion of gas. Now, before dealing with what is the work done in a free expansion, let's first understand what exactly we do mean by the term as a free expansion. Okay. Now, in order to understand that, let's say that we have a particular cylinder, and this cylinder is been fitted by a piston. Let's say this is the piston that we are going to take, and we have set it over here. Okay, so when you are going to set this particular piston, this particular cylinder, let's take into consideration that it has 1 mole of ideal gas. Okay, now the second consideration that we have to note is that this 1 mole of ideal gas, of course, it is going to have some amount of pressure from the inside. Correct? Let us say that that is PRN, that is nothing more than the internal pressure. Okay, now if this is considering as this particular system is kept in an atmosphere, there is certain amount of pressure that is going to act on this piston from outside, which we consider it as an external pressure. Okay, so let's say PEX is going to be referred as an external pressure. Right? Now, for a moment, let us say that the external pressure, what is there, this external pressure is equal to 0. That means there is no external pressure acting on a piston. This happens only and only when we take off all the air and we subject this particular system to a vacuum. So therefore, a vacuum condition is created outside the system. That means there is no pressure on the outside wall of this particular piston. Correct. So if there is no pressure that is acting from the outside, naturally my internal pressure is going to be greater because external pressure is 0. Correct. So when the external pressure is 0 and the internal pressure is of course going to increase, the piston is going to slightly move outwards. It goes on moving outwards now. As it goes on moving outwards, then what is happening here? The work is done on the piston. Correct. But this time, we are going to refer taking this into consideration. That is, the external pressure is equal to 0. So, at this particular condition, the work is equal to minus of Pex into delta V, right? This is what expression we have. Now, as we have said that it is kept in a vacuum, that means Pex is equal to 0. So therefore, as this particular term is 0, therefore the work which is done is going to be 0. Okay, so whenever we take a look into the work done in a free expansion, okay, whether this particular work is reversible or whether the work is irreversible, if it is happening in a vacuum, if it is happening during a free expansion, the work is going to be 0. Okay, so whether this particular work is reversible or whether this particular work is an irreversible process, in both these conditions, the work is going to be 0 if the expansion is occurring in a free state. Correct. So this is how we need to understand. Please try to imagine things while you are studying. This is a perfect way to study thermodynamics. Okay, so let's go with the next concept. So the next concept that we require in order to study is going to be the heat. Right? Now, in order to understand heat, first we need to understand the temperature. So, basically speaking, a temperature. This temperature is nothing more than it is the degree of measurement. It is a degree of measurement as how hot or how cold the particular body is, or the hotness or the coldness of a system. So, the temperature is nothing more than a measurement of hotness or the coldness of the system. And the most important thing is now. Okay, and the energy flow between the system and surroundings. And this energy flow as what we have. This energy flow depends upon the degree of the temperature differences. Right? Now, for example, let us consider that we have at this particular moment a particular glass containing ice. Okay, if we do have that, we'll understand it in a much more better way. Now, let us say that this is a particular glass. A glass is nothing more than our system, right? Now, as this particular glass contains certain amount of ice cubes, so what generally happens? The temperature inside the gap, this particular system or the glass, is lower when I consider to the temperature surrounding to it, right? Now, you need to understand that whenever there is a change in the temperature between the system and the surrounding, the heat is going to flow. For example, if I hold this particular glass somewhat like this, yes, my palm is going to feel its coldness. Why is this particular palm feeling cold? Is because there is a temperature difference. The heat is being absorbed by the glass. When my body loses heat, it will start feeling colder, right? So therefore, the heat energy from the palm is going towards this particular container. This is how it happens. So, as a result of which, what is going to happen? There is a temperature difference. Whenever there is a temperature difference between the system and the surrounding, the heat is going to flow, right? Now, whenever the heat flows, the heat is going to flow, okay, the energy flow between the system and the surrounding because of the temperature differences. Okay, so there is a complete temperature difference as there is a temperature difference, the heat usually flows. Right. So therefore, now there are two methods, there are two possibilities. Either the energy enters into the system or the energy flows outside the system. Same is in relation with respect to heat. Either the heat flows into the system or either the heat flows outside the system. Okay, so if we consider this as the particular system, okay, let's say this is a system as what we have, and now if this particular system is going to absorb the energy in the form of heat, that is, if the heat is going to flow into this particular system, then this particular heat is going to be taken as positive into consideration, because we are supplying the heat to the system from the surroundings, right? In the case if this particular system is going to lose heat energy, for example, we can take a cup of tea. Now, I'm not going to take a cup of tea again. Okay, you need to understand that. So, if we are going to take a cup of tea, what is going to happen is, if it is hot, the temperature difference again between the system and the surroundings. System has more degree, correct? It is quite hot than the surroundings. At that particular point, the energy flows from this particular system to the surroundings. Now, when that happens, if the heat is been given from the system to the surroundings, then this particular heat is going to be taken in the form of negative. Okay, so if you transfer the heat to the system from the surrounding, it is going to be taken as positive. If the heat flows from a system to the surrounding, the heat is going to be taken as negative. Okay, now whether it is positive or negative, you should know that this heat, okay, the certain points of heat you need to know that this heat is represented as Q. Secondly, this particular heat is a path function. Remember this. It is a path function. That means it depends upon the particular path followed by this particular system in order to achieve that point. Okay, so whether it is the heat transfer or the heat that is exchanged between the system and the surroundings. Let us say that when there is an exchange of heat, delta T is a change in temperature. Naturally, there is going to be change in temperature. Let us say that we have the same ice-filled container. Okay, so what does the ice-filled container does? First, the temperature is quite lower. As it starts taking energy from the surroundings, temperature naturally comes to a point where it is equal to the surrounding temperature. So there is a temperature difference, right? Starting it was very lower, and now after exchanging the particular energy, it has risen to a particular height. Okay, so now what is going to happen? Delta T refers to the change in the temperature when we consider the initial state and the final state of the system. Okay, so if I'm going to write it over here as Q is nothing more than the heat energy. Okay, if Q refers to heat energy that has been transferred to the system or from the system to the surroundings, doesn't matter. So if that is condition is equal to coefficient into delta T. Remember this particular expression is very, very important. It means that the heat energy that has been transferred to a system is equal to a coefficient. What is coefficient? It's something more than a constant. Okay. Into what is a change in the temperature. If the heat is transferred to the system, how much temperature difference was there? Okay. And now, coefficient. Coefficient depends upon how much this particular substance is. What is the composition? What is the size? What is the nature? So, the coefficient over here, this coefficient, okay, it is like a constant. Okay, so this particular coefficient, depends upon size, depends upon composition, and of course it depends upon the nature of system. Okay, so kindly remember this particular point. That is, heat supplied is equal to coefficient into the change in temperature, because this particular expression we are going to take further. Let's start with the next concept. The name of the next concept you will understand once we start solving. So in the previous case we have seen that if Q is the amount of the heat that is going to be transferred, so this particular Q is equal to coefficient into the change in temperature. This is what we had already seen. Correct. Now, this particular coefficient has a particular name, and the particular name for this coefficient is called as the heat capacity. Okay. Now, in order to understand this particular heat capacity, let's take into consideration of a system. Let us say that we have a particular system over here. And in this particular system, let us say that we have taken a particular type of a liquid. Okay. Now, I'll measure its temperature first. Let us say the temperature of this particular condition is T1. And now, what shall I do is, I am going to take this particular system and I am going to supply heat energy to this particular system. I am going to supply the heat energy until and only till that point where it is going to increase the temperature till T2 in such a way that the difference between the two temperatures is just 1 degree Celsius. So in short, I have supplied the energy in such a way that the difference in the temperature is 1 degree Celsius, right? So this heat capacity is going to be defined in this particular term as the quantity of heat required to raise the temperature of system. This is the system as what we are speaking about, right? So the quantity of heat that is required to raise the temperature of the system by 1 degree Celsius. So by 1 degree Celsius, and that is called as your heat capacity. Okay, and this heat capacity is denoted by C. Okay, so the heat capacity is denoted as C, and therefore we have a new way of expressing it, that is Q is equal to C into delta T. Please note that this is a capital C over here. Why I am stressing on this, you will understand it in a few more minutes. Okay, so this is our point where we need to observe it in a detailed way. Okay, so Q is nothing more than the heat that is being supplied. C is our coefficient, which we call it as the heat capacity, into T. So quite naturally, if C is greater, remember, if C is greater, if the magnitude of C is higher, quantity of heat that is required in order to raise the temperature by 1 degree Celsius is huge. Okay, so if C is higher, or if its magnitude is high, then what is going to happen? If the magnitude is high, then more amount of heat is required to increase raise the temperature of system by 1 degree Celsius. This is what we need to know. Now, heat capacity, there are two types. One is called as a specific heat capacity, and the another one we call it as the molar heat capacity. So there are two types. One which we call it as specific heat capacity. Okay. So first one what we have is a specific heat capacity, and the second one is what we have is a molar heat capacity. Let us write down over here molar heat capacity. Okay. Now first let us understand what exactly do we mean by a specific heat capacity. So specific heat capacity is nothing more than a heat capacity. Okay, it is simply like a heat capacity for a unit mass, but let us put it into a much more better manner. So heat capacity is the amount of heat required to raise the temperature per unit mass. This is very important now. See, what we are speaking here, per unit mass. You are going to increase the temperature of per unit mass by 1 degree Celsius, or whether it is Kelvin. Okay, so specific heat capacity is nothing more than the amount of heat that is required in order to raise the temperature of a system having a unit mass by 1 degree raise in its temperature by either it can be given in form of Celsius or Kelvins. Okay, while on the other hand, molar heat capacity. So molar heat capacity is nothing more than the amount of heat required to raise, or you can also say as increase, okay, the temperature of 1 mole system. That means when you have a system which contains 1 mole of either gas or whether it is a solid or whether it is a liquid. Okay, doesn't matter. But condition is when you have a system and that particular system has a 1 mole of substance present in it, and that time when you supply the quantity of heat to it, that particular capacity, heat capacity, we call it as a molar heat capacity in that particular case. Okay, by 1 degree either Celsius or by Kelvin. There is another way by which we can also call it, and that is for molar heat capacity, it is nothing more than the heat capacity. Now we are coming over here back to this particular point. Okay, heat capacity. So the heat capacity of 1 mole of substance. Alright, so heat capacity of 1 mole of substance is nothing more than the molar heat capacity. Now finally, we need to understand that how are we going to give a relationship between the specific heat capacity, the heat transfer and the temperature change. So therefore, we have an expression which we give it as Q, which refers to the heat transferred, is equal to C. Now this C is a subscript, okay, small one. So into M into delta T, where C represents specific heat capacity, M represents the mass of substance. Of course, you know about the other two. that is Q is nothing more than heat, delta T is again the change in temperature, right? So let us go further with the next point. For the final point, let us understand what is a relationship between the heat capacity of a system and the molar heat capacity. Okay, so let us say that we have a system. So let's say this particular system is going to have n number of moles. Okay, so this particular system has n number of moles. So for this system, if I'm going to say for this particular system, C is the heat capacity. Alright, if C refers to the heat capacity, and if I need to find the molar heat capacity, this is the molar heat capacity. So the quite the relationship is between these two can be given as C. Okay, let us put it as small c m, that is nothing more than the heat capacity for the molar. Okay, molar heat capacity is equal to heat capacity of a system divided by the number of moles. So remember this is the expression which will give us a relationship between the molar heat capacity and the heat capacity of a particular system which contains n number of moles. Okay, so we'll meet you in the next video. Thank you for watching. Do stay safe. Take care.